All right, students, so I'm going to move on to the next part of this lesson about alternating series. So we're going to talk about remainders in an alternating series. It's kind of good to just show an example to explain what all this stuff is. So the first thing we're going to take a look at, I want to just kind of talk about what this means. And I'm going to use an example over here on the side to explain that, and then what the neglected term is and what this inequality means. So I'm going to go over to the side and just use this as an example, okay? And you can write this down if you want to, just pay attention to this. So this would be an infinite alternating series, and basically what's happening on this, if you wrote out the terms, and I'm not going to go through the details of that, but if you wrote out the terms, you can see this, and this is a convergent alternating series, also by the alternating series test. So I want to show you a couple of things on here. So let's say, for instance, that we were wanting to estimate the value of this convergent series, right? Just estimate it. Well, one way that we could do this is we could do a partial sum, all right? So S of 4 just represents a partial sum, and that partial sum would be 1 minus a fourth plus a ninth minus 1/16, and we could just do that. I'm going to go ahead and just do that on the calculator real quick and just get decimal forms of this. So I'm going to go 1 minus 0.25 plus 1 over 9 and minus 1 over 16. Okay, so that would be a partial sum. Let's just write that out, about 0.7986, and then you have repeating ones like that. Okay, so that would be a partial sum. That would be an estimate of the value of this series, okay? So now the next thing I want to kind of point your attention to is this. This part right here would be what's left over in the infinite series. We call that R of 4, all right? So what we would get is R of 4 is the remaining term. So we call that the remainder of your series. And that sum would just be, and of course we can't really do that, but we would have 1/25 minus 1 over 36. It would just be, you know, what's left over. That would be the remaining sum right there. And then the other thing that we have is, if we looked at the whole entire thing, we would call that S. So S is equal to the actual sum of the infinite series. Okay, so that's what everything means in our definitions, like this. And then this term right here is going to be what we call the neglected term. Okay, that's after S of 4, so that's what we call the neglected term. All right, so far so good. Okay, just a little bit of terminology on this then. All right, so if we go over kind of to our definition now, we're going to look at what a few things mean in these definitions then. Okay, so I've explained what the remainder is, and again, the remainder is just the value of the series and minus the partial sum. Okay, so that's what I tried to show you is what that is right there, all right? So a couple other things, like in this example, S would be equal to the actual k equals 1 to infinity of negative 1 to the k plus 1. I think I got a variable mismatch in there. So I got k plus 1 there. So we got this over k to the second. Okay, S of n would just be a partial sum, so that would be k equals 1 to some number n of mismatching my variables again here. So we'd have this k equals 1 to n, and then negative 1 to the k plus 1 over k to the second. Okay, so that's what we have there. And then the remainder would just be the difference between those two things then, all right? So what you get in this particular statement here, the magnitude of the remainder is basically just the error in approximating the sum of the series. So if you look at what I kind of have over here, this part right here, what's left over, that's really what the error is. All right, so that would be the error. That if you approximate the series by the first 4 terms, then what's left over would be the error. Okay, so that's what that is saying. All right, so let's see. Going on through here, here's kind of the key thing that we're going to talk about here is this inequality then. All right, so it turns out that this part right here is the remainder. That's what we talked about. That's the value of the series, of the infinite series. Okay, and then this part right here is the partial sum. Okay, so it turns out that that is less than or equal to the difference between these two partial sums. All right, like that. And I'll kind of explain with my diagram what that means there. So the remainder, which would be this whole thing right there, is going to be always less than or equal to the partial sum, this part right here. If you look at this right here, that would be s of n plus 1 would be s of 5, so it would be the sum of those fifth terms, minus s of 4. Well, that would be the neglected term. So what you end up getting on this is this just ends up being a sub n plus 1. So in this case, that would be the fifth term. So I want you to just kind of use this example to help you understand this, because this is very abstract. This shows this in a more concrete way. So again, for my example, what we're showing there, we're kind of showing that r of 4 is equal to basically s minus this entire sum minus s of 4. Okay, so that's what that's given us right there in this inequality. Okay, well that is less than or equal to s of 5 minus s of 4. Okay, so what that is, s of 5 is this thing, s of 4 is this thing, so it's kind of like that. So that would just be equal to, in this example, 1/25th, which would be the neglected term. We call that the first neglected term. So that's the idea there. All right, so that's where that inequality comes from. And without really doing a proof of this, you could see that the remaining terms of this series end up being less than 1/25. All right, that can be shown like that. But I want to just give you an idea with a concrete example of what this is saying. Okay, so we're going to go down and we're going to begin to do an example on this. So I'm going to move down here. You can pause the video if you need to. On here, we're going to do a couple of examples that demonstrate this idea of estimating the value of a series. Now, what we're going to do on this example right here is we're going to approximate the sum using the fourth partial sum, and we're going to estimate the error in approximation. Okay, now this series right here, I didn't write on your notes, but this is a convergent series. I'll show you how we can prove that. And the value is pi over 4. This is a kind of a well-known series that just goes 1 minus a third plus a fifth minus a seventh plus a 9. And what's really cool about this is eventually that sum is pi over 4. So you got pi showing up in this infinite series, which is really interesting. This series, by the way, could be used to approximate pi, to actually just build pi, because if you multiplied both sides by 4, you would get pi is equal to 4 times the series, k equals 1 to infinity, of negative 1 to the k plus 1 over 2k minus 1. So how cool is that? That's what pi is. Pi is the value of that infinite series times 4. Okay? All right, so let's go ahead and let's work with this a little bit. And the first thing I'm going to do on this problem is we're going to show the convergence. So we're going to start by showing that this infinite series converges. Just want to go over that real quick. Okay, and we'll go ahead and we're going to write out some of these terms on here too as we do this then. So let's go ahead and let's just write out these terms, okay? So the first term, if you let k equal 1, you can do a lot of this in your head. If k is 1, you would have negative 1 to the second over 2 times 1 minus 1. So that's 1 over 1. Then if you go to the next term, if you go to k equals 2, that would be negative 1 to the third over 2 times 2 times 2 minus 1. A lot of this stuff you can do in your head, or you can just kind of write out the work like that. So this would be negative, and that would be 1 over 3, like that and so forth. Okay, so I was kind of writing the terms out here. So we have 1 minus a third, and then the next term in this series would be back to positive. It would be 1 over 5, and then it would be 1 over 7 plus 1 over 9. Once you kind of get the pattern going, then it's easy to complete that then. And I'll write out a couple of more terms like that then. All right, so we got the alternating signs, and this is just odd numbers. If you look at that, 2k minus 1 is an expression for odd numbers. Okay, so we got that. All right, so we want to write that out. So remember, we do two things if we show an alternating series converges. First thing we do is we show that 0 is less than a sub k plus 1 is less than or equal to a sub k. So we neglect the part that makes it alternate. Okay, so we know that since k is 1, you're always going to get, if you neglect the part that makes it oscillate, you're going to get positive terms. So this is going to be greater than 0. So we're just going to work on this part right here. So a sub k plus 1 would be 1 over 2 times k plus 1 minus 1, and we're going to try to show that that's less than or equal to 1 over 2k minus 1. Okay? So there's this thing that shows up a lot. If you go through and work this out, this would be 2k plus 2 minus 1. So that would be 2k plus 1. Just a little basic algebra, less than or equal to 1 over 2k minus 1. Okay? Well, this is a bigger denominator than this is. Okay? So see, these two things right here are equal. This is adding 1, that's smalling 1, so that's good enough. So you can just say, okay, that's a bigger denominator, therefore we have non-increasing terms. Okay, in looking at that. Step 2 to test for convergence is real simple. Alternating series test, we work out the limit as k goes to infinity, not x. Sometimes I can't talk and write at the same time. So k goes to infinity of 1 over 2k minus 1. Okay, that's pretty obvious that that's equal to 0. Okay, because that's a 1 over infinity form there. Okay, so therefore, we know that our series converges by the alternating series test. Okay, I'm giving you what it converges to in this case. I'm giving you that. A little bit later in the class, another week, once we get into power series, then we'll start learning how to compute some of these things. Okay? All right, so we got that. So now we know it's convergent. So what we're going to go ahead and do is we're going to just kind of list out these partial sums. All right, so I'm going to go ahead and work out the partial sums. All right, and we can use a calculator to do this and get this accurate and everything. So S of 1 would just be the first term, 1. S of 2 would be 1 minus a third, so that's equal to 2/3. S of 3 is going to be 1 minus a third plus a fifth. Okay, I think that'll be 13 over 5. And then we'll go all the way up to S of 4 because the directions of the problem say we want to use the fourth partial sum. So it's 1 minus a third plus a fifth, and then minus 1/7. Okay, so if I do that, I'll end up getting this then. So I'm just going to take the 13 over 5 from the previous step, and then I'm going to subtract, 13 over 15. So I do 13 over 15 minus the 1/7. Okay, I'll go ahead and change that to a fraction. Okay, and that is equal to 76 over 105. And I'm going to go ahead on S of 4 and just write out the decimal. That's 0.7238095 238. Okay, like that and so forth. All right, so we got that to begin with then. All right, so you can use your calculator to find the partial sums. Just doing that to save yourself time. You don't have to do all that arithmetic in this class. Okay, so what we're going to do is we're going to end up looking at comparing this to the actual answer, which is pi over 4. So let's do pi over 4 on the calculator. So I'll just take pi divided by 4, and I'll write out about the same number of decimals. So that is 0.7853981634. Okay, so if you notice on this, well, it's accurate within one decimal. Okay, so what we're going to end up doing on this problem here is the directions of this problem say approximate the error in estimation. That's all we're going to do is that. Okay, so what we'll end up doing on this is adding four series. Now remember or 4 terms. The error in approximation, which we've talked about before, you always just take the exact answer, which we know is pi over 4, minus the approximation, which we got, all over the exact. And then that would be telling you basically how accurate this is. Okay. So let's see on this. What we'd end up having is the exact answer is pi over 4. The approximate S of 4 is 0.7238095238. And then all over the exact pi over 4. So I'm just going to do that on the calculator. And that'll give us the error in approximation. Okay. So if we go pi over 4 and minus the 0.7238095238, get that, and then divide that by pi over 4, that'll give us the error in approximation. Okay, so that error is approximately 0.0784170914. Okay, so that's the remainder. That's the difference on that. Your error in approximation is going to be this value right there then. Okay, so we're pretty close. We're close within, the first decimal's accurate. So actually we're just kind of comparing the difference between that in a ratio with the exact value like that. All right, so that's a good way to start learning about remainders like that then. Okay? Okay, going to pause this for a second. Okay, so I wanted to show you one other thing before I leave this problem. See, what we just did is we just did the error in approximation, and that'll be less than the next term. Okay, so I want to add on just a couple other things on here. So according to the property we learned, it says that R of 4, on this problem, since we're doing 4 terms, the remainder of 4 terms would be the same thing as S minus S of n. So what that would be is the actual sum is pi over 4, and then the partial sum S of 4, but that's going to be less than or equal to the next neglected term. Okay, so if you look at this, if you go like 1, 2, 3, 4, 5, that's your neglected term. So that's going to be less than or equal to 1/9. And you can verify this on the calculator. That's what I was doing when I paused the video, is if you do pi over 4 minus, this is the partial sum, you get that, and that's less than that next, can't talk, neglected term. Okay, so that's the idea with that then, all right? Okay, moving on to the next example. Another interesting series on this next example here. This is another convergence series, and on this one we're going to work a little bit with the error and approximation using the remainder. This is another interesting series that it's convergent, and it's 1 over e. Okay, so actually if you took the reciprocal of both sides of this, e would just be the reciprocal of the value of that series. That's interesting. So e can be expressed as an infinite series. So in this problem, what we're going to do is determine how many terms how many terms of the following convergent series must be summed to be sure that the remainder is less than 10 to the negative 4 in magnitude. All right, so we do have the value of this convergent series as 1 over e then. Okay, so we're going to go ahead and begin this problem by writing the terms of this series out. Okay, so I'm just going to kind of write these out. You can do this in your head. That's a negative right there. So I'm going to do a little bit of scratch work over at the side. So we would have negative 1 to the 0 over 0 factorial would be 1 over 1. So that first term is 1. The next term would be negative 1 to the 1 over 1 factorial. So that's negative 1 over 1. So that's minus 1. And then we would have negative 1 to the second over 2 factorial. That's positive 1 over 2. And so forth. Okay, now I'm going to just kind of write the rest out. I just wanted to kind of show you how that goes. I don't want to spend a lot of time on this. You could pretty easily go through and calculate these things out. That's 1 over 24. And then when you get to the next one, let's see, this is really just giving, you kind of have 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and then 5 factorial is 120. And by the way, I think I've shown this in previous videos, but if you're calculating out a factorial, like if you want to do 5 factorial, you go 5, math, probability, and option 4, and that'll calculate that out for you. So I'm just going to write one more term out. So this would be now a minus, right, since you have an alternating series, this would be minus 1 over 120 like that. Okay? Now, what I want to do on this is, of course, the series just kind of goes on and on like this. Okay, then you would have the term negative 1k minus 1. I'm going to erase this scratch work here. All over k minus 1 factorial. And then the next term after that would be negative 1 to the k over k factorial. Okay, like that. All right, so that's how, and what I'm doing there is, this is, the formula you're using, that would be the previous term. That's why I have k minus 1 like that. Okay, so what we're going to do on this is it says, if you kind of look at writing this series out, this right here, all the way from there to there, is going to be S of n. Okay, so what that is that's a partial sum of the first, in this case, of the first k terms. Okay, all right, so we have that. So what I'm going to do with here, or n terms, I'm going to write that as n terms, like that. This part right here would be the remainder. Now remember, this would keep going on and on forever right here, so we're going to call that r of n, and that's equal to the actual value. Now see, we know that on here. We know that actual value is 1 over e minus the partial sum right there. Okay, so that's the error. That gives you the error in approximating the value of this series if you use n terms. Okay, so we have that then. So what we're going to do is we're going to set up an inequality. So the absolute value of the error, that's equal to the remainder. That's the meaning of r sub n. That's equal to the actual sum minus the partial sum. That's less than or equal to the absolute value of a sub n plus 1. Okay, now what that is that's the first neglected term. Okay, and if you look at that on this particular thing here, all right, the first neglected term, then we can go ahead and write that out in a certain way. Okay, so what we're going to do is we're going to set this up like this. Now, we're looking at the series 1 over k factorial like this. So what we're going to do is we're going to set up this inequality. We're going to look at 1 over n plus 1. That's just the next term going up, and that's supposed to be less than 10 to the negative 4. So I'm going to write this as 1 over n plus 1 less than, and then we'll write this as 1 over 10 to the 4th power like that. All right? Now I'm going to use it this way, and we're going to count out the factorials, and I'll show you how we can figure out how many terms it's going to take to make the remainder less than 10 to the negative 4. Okay? So that's kind of the idea on this is your neglected term, and we're doing the absolute value of that. Numerator is 1, and what I want to do is I also want to show you this. Okay, so I wanted to show you this, kind of where that n plus 1 is coming from. The numerator is always 1, and we're doing the absolute value of this neglected term right here, so that's 1. But what we're doing is this. If you kind of write out a factorial, what you would have, you can write it out 2 ways. You can write it out this way, or you can write it out this way. 1, 2, 3 gets bigger and bigger. You just get up to k, and then you get k plus 1 and so forth. So that's where I'm writing that as n plus 1. So I'm now going to set that less than 10 to the negative 4. And what we're going to do is work with this inequality over here. Okay? All right. Let me rewrite this, and we'll show you what we're going to do on this. So we have 1 over n plus 1. We're trying to find the value of n that makes this remainder, this neglected term, first neglected term, less than 1 over 10 to the 4th. So let's work with this inequality. What we could do is we can multiply both sides by 10 to the 4th n plus 1 to rid ourselves of the fractions. Okay, so we'll have that. We'll have this. So that's going to end up giving me 10 to the 4th is less than n plus 1. Okay, if I want to subtract 1 from both sides, I got 10 to the 4th minus 1 is less than n. And if I do this on a calculator, you don't need a calculator, that's 10,000 minus 1. So we would get n has to be greater than 9,999. So in other words, we need to get n, the next term after 9,999 would be 10,000. Okay, now, what we're going to do is, since we're working with a factorial, that's the reason I'm going about the problem this way. Remember, we're working with the series 1 over k factorial. So we're going to work this out like this. All right, if we end up having 0 factorial, we know that's 1. We're just going to write this out. We have 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, 6 factorial 720. I'm not doing this in my head. I already have this worked out. 5,040. All right, and I keep going on this now. When I get to 8 factorial, see, I get to 40,320, and that's greater than that 10,000 then over here. All right, so it's greater than the 9,999 like that. So that's where we got to get to, is we got to get all the way up to 8 factorial on this then. All right, so if you look at how many terms of the series you must do, okay, well, on this one, count the terms of the series. This would just be 1, 2, 3, 4, 5, 6, 7, 8, 9. So when we get to the 9th term of the series, the series must be summed, so that remainder is less than 10 to the negative 4. That's why I wrote the factorials out and did it this way, because now I'm just trying to figure out what value of k over here gets bigger than 9,999. So that's how that problem would go, and that's how you'd work that out. Okay? All right? Okay. That could be a little tricky. Okay, next problem, I'm going to do one more example of this. It's just very similar. This is another well-known convergent series. It's got pi in it also. So we're going to look at that. We're going to do exactly the same thing we did on the previous problem. Find the number of terms of the series that must be summed such that the remainder is less than 10 to the negative 4. Okay? So a good way to start the problem is just writing out the terms of the series, all right? I'll do a little scratch work at the side. We start at k equals 2. So we have negative 1 to the 2 plus 1 over 2 to the second. That'll be negative 1 over 4. So that's your first term in your series. Usually after you count out a few of these, you start seeing the pattern. The next one would be negative 1 to the 3 plus 1 over 3 to the second. That'll be positive 1 over 9. So all it's doing is it's alternating, and then these are squares. So then your next term would be 1 over 16. You'd have 1 over 5 to the second, 1 over 6 to the second, and so forth like that. Just kind of carry it out as far as you want to. Now what you're going to have is blah, blah, blah. You're going to end up kind of going like this. And eventually, we'll end up on this. We'll have like the series negative 1 to the k plus 1. This is what you were given. And then the next item in this would actually be this. If you went to the next item, and I'm going to erase that like that, then we'd kind of go like this. We'd end up having negative 1 to the k plus 2, because that'll go up 1. And then this will go up to k plus 1 to the second power like that. Okay? And you can write it out like this. You could also write the previous term. On the last problem, I just decided to write it this way. That's really, you don't have to do it that way. Okay, so what I'm going to do is just kind of highlight a couple things right here. So this thing right here, what would that represent? Right, that would be the partial sum. Okay, and what does this represent? Okay, that is the remainder of n, which is s minus s of n. Okay, this is the actual value. The actual value of this series I gave you as pi squared over 12. And then this would be the s of m, whatever that partial sum is. Okay, and then of course the whole entire thing is what s is. So the actual sum of that series is pi squared over 12 like that then. Okay, so what we're going to do is we're going to kind of work out what we've been doing. We know that the error in approximation, the absolute value of that error in approximation, ends up being less than or equal to the first neglected term. So this would be the first neglected term. I'm going to use this form like this. So that's going to be less than or equal to negative 1 to the k plus 2 all over k plus 1 to the second. Okay, like that. All right. And we don't really have to worry about this. I didn't really need to write this out here. That's just going to be 1 because we're not looking at that part of the alternate series. Okay. So what we end up having is we have this right here. All right. And we want that to be less than 10 to the negative 4. That's what the problem again stated, was the number of terms, the remainder, which is this, the remainder is less than or equal to the first neglected term, which is this. So you're going to have to work with this inequality. So let's work with this inequality. It's very similar to the last problem. We'd have 1 over k plus 1 to the second is less than 1 over 10 to the fourth. Okay, so what I'm going to do on this is clear my fraction. I'm going to multiply by 10 to the fourth, k plus 1 squared, both sides. You can certainly do this in your head. That's easy enough. Okay, that'll cancel that out. So you end up getting 10 to the fourth is less than k plus 1 to the second power, like that. Okay, and of course 10 to the fourth is 10,000. Then we have k plus 1 to the second power like that then. Okay, so what we can do on this is we could actually just do a square root of both sides. Okay, and if we do square root of both sides, the square root of 10,000 is 100. That would be less than just k plus 1. Then you can subtract 1 from both sides, so you get 99 is less than k. So k would have to end up being equal to 100 terms then, like that. So what you would end up having is you would just say 100 terms of the series must be summed so that the remainder is less than 10 to the negative 4. All right? Okay, so I want to show you something on this. All right? So let me show you this Desmos thing, and this will help you make sense of this stuff better. So I highly recommend you get on that Desmos and check this out. So let me show you what I'm going to do on this. I'm going to go to the Desmos Calculator. All right. So I put in the series. This is the series we're doing. I think on my handout I meant for this to be k equals 1. All right. So I put in the series. We have that. And remember, we found that at 100 terms, the series has to be summed up. It's got to be accurate within by 10 to the negative 4. So let me show you what I did. On my calculator, if you look at your notes, this is the value of that convergent series, 0.82246, blah, blah, blah. So if you look at 100, look at this, 0.8224, 0.8224. Within 4 decimals, we are accurate. Then we start losing our accuracy, all right? And what will happen as you go out to 1,000 terms, well, you start getting closer and closer and closer the further out you go. So that's the idea, okay? And I don't know on Desmos if I can put in 99. I guess I can put in different things right there. Okay, so notice the accuracy partial sum S of 99 does not have the same accuracy that this does. So 100 would be the first term that has an accuracy of 10 to the negative 4 decimal places. So I hope that helps you make sense of this. Okay, all right, so that'll wrap up the second part of this video. Hope you enjoyed this. Hope this helps you to understand what we mean by remainders and neglected terms. And we're basically looking at how we can approximate errors, and we can approximate the sum of a convergent series. All right, hope you enjoyed. Good luck.